Hello students, myself Miss Akanksha Sangdev Gurule. I welcome you all again in our second semester. So in the second semester, in this course particularly, we are going to study inorganic chemistry. So the subject code for the inorganic chemistry is CH201. In this lecture, we are going to start with the first lecture, with the first chapter, that is atomic structure. In this lecture, we are going to see the introduction to syllabus and quantum mechanics. So now let's begin with our second semester and with our first chapter. So as I have introduced, this course has a course code CH201 inorganic chemistry. So there are three chapters mainly in this course, that is atomic structure, periodic table and periodicity of elements, chemical bonding. So this whole inorganic chemistry is for 2 credit. So in the atomic structure, we are going to study the main topic of the chemistry, that is the quantum mechanics. So in this, we are going to study why we need to study the quantum mechanics. In that, particularly, we are going to study the topics black body radiation, photoelectric effect, wave particle duality, the particle character of electromagnetic radiation, the wave character of particle, diffraction by double slit, atomic spectra, review of Bohr's theory and its limitation, and also we are going to study the Heisenberg's uncertainty principle. So in the quantum mechanics, particularly, there is a Schrodinger equation. So we are going to study the Schrodinger equation. There is also time independent Schrodinger equation. Also, we are going to study the various terms introduced in the Schrodinger equation. We are going to study what is the significance of wave function, or what is the significance of probability differentiation, radial nodes, angular nodes, total nodes. Also, we are going to study the significance of quantum numbers. That is a principal quantum number, spin quantum number, and so on. Also, we are going to see the shapes of atomic orbitals. That is why the shape of s orbital is spherical, why p orbital is dumbbell shape. So from where it is arise, that all we are going to study in this chapter. So in the next chapter, that is periodic table and periodicity of element, we are going to study the periodic table. Also, we are going to study the periodicity of elements. So in that we are going to study rules for filling the electrons in various orbitals, electronic configuration of atoms, stability of half-filled and completely filled orbitals, concept of exchange energy, relative energies of atomic orbitals, and also anomalous behavior of electronic configuration. In that we are going to study the trends in periodic table that occurs depending upon the shielding effect, atomic or ionic radii, crystal radii, covalent radii. Depending on these factors, how the trends are changing along the group or along the periods. Okay. The next chapter is chemical bonding. So in the chemical bonding, we are going to study the various theories. That is the valence bond theory, molecular orbital theory, types of chemical bond, that is ionic bond, covalent bond. In ionic bond, we are going to study the lattice energy, Born-Landis equation, Born-Haber cycle, and its application, polarizing power and polarizability. That all we are going to study in ionic bond. Also in the covalent bond, we are going to study the VSEPR theory, assumptions of VSEPR theory, and how to apply or how to gain the geometries of the molecule according to the VSEPR theory. That all we are going to study in this chapter, that is chemical bonding. So now moving towards our first chapter, that is atomic structure. In the atomic structure, we are going to study the quantum mechanics. So first of all, there are two mechanics. That one is a classical mechanic and another is a quantum mechanics. So in classical mechanics, we study only the macroscopic property. So what are the macroscopic property? Such as Earth, Moon, planet, cricket ball. So all these objects study which are macroscopic, which can be able to seen by the eyes, are done in the classical mechanics. Whereas in quantum mechanics is the study of behavior of matter and energy at this subatomic scale. That means at microscopic level. So in classical mechanics, the study is of macroscopic property. In quantum, it is a microscopic property. So you have to remember the difference between these two words, macroscopic and microscopic. So next is why we should study the quantum mechanics. What is the importance of quantum mechanics? So quantum mechanics is the branch of science that deals with atomic and molecular properties and behavior of matter on microscopic scale. Okay. So in quantum mechanics, we are going to study the properties of photons or the behavior of photons, electrons, protons, which are microscopic. So in this, the study is limited to the microscopic scale. So what is the need of quantum mechanics in various branch of chemistry? So we will see branch wise the need of quantum mechanics. In physical chemistry, it is used to interpret the molecular spectra by allowing experimental determination of molecular properties like bond length, bond angle, dipole moments. That is, in physical chemistry, whatever this molecular spectra we obtain, we have to interpret it. So why we have to interpret it? To determine the bond length, bond angle, dipole moment of the various molecules. So for that, we need a quantum mechanics. The next is to calculate the property of transition state in chemical reaction used in the estimation of the rate constant. So to determine the property of transition state, whether it is a stable, whether it is unstable, so how it behaves, that all study is done in the quantum mechanics. The next is in organic chemistry. So in organic chemistry, it is used to estimate the relative stability of the molecule, to investigate the mechanism of chemical reaction, to predict the aromaticity of the compound. These are some examples where the quantum mechanics is used. So in inorganic chemistry, to predict and explain the property of transition metal complexes and metal ions by using the ligand field theory. Also to study the properties, structure and symmetry of inorganic compounds. So inorganic compounds are complexes in which one atom is linked to the another atom by various bonds. So what will be the symmetry of that molecule? Whether it is a tetrahedral, it is a trigonal, or how it appears. That symmetry of that molecule is deduced by applying the concepts of quantum mechanics. So here the quantum mechanics is applied. So according to the classical mechanics, energy is emitted or absorbed continuously. That means energy, as we get energy, we absorb it continuously. We are absorbing, or any object is absorbing that energy continuously. But according to the quantum mechanics, energy is emitted or absorbed not continuously but discontinuously in the forms of packets of energy known as a quanta. This was according to the Planck's theory and experiment. So as we think that by classical mechanics that energy comes, we absorb it. Whatever we need, we absorb it. But according to the quantum, it is absorbed or emitted in the form of packets. That means any object absorbs the one quanta of energy or it emits the two quanta of energy. That is the unit or that is the packets of energy known as a quanta. So at the atomic level, light waves have particle-like property and atoms as well as subatomic particle such as electron has wave-like property. So this you will understand in wave particle duality topic that the wave has a particle or the uh, light wave has a wave as well as particle like a property. So as we have seen the need of quantum mechanics in the various field of chemistry, the quantum mechanics is also used in the electronic revolution. It will give us a deeper insight into the granularity of physical structure of the world. It is also used to investigate or diagnose the tools such as electron microscope, the PET and the MRI scan. It is also applied to the thermodynamics. So these are the various uses or the need of quantum mechanics. It is also used in the photovoltaic cell. So there are various applications of quantum mechanics. Okay. The next topic that is a black body radiation, which is the key topic in the quantum mechanics. So what is a black body radiation? So when the radiant energy falls on the surface of any body, what happens? Either it gets reflected from that body, either that body absorbs that radiation, or either it transmits that radiation. These are the three factors that body can do when it comes in contact with the radiation energy. That is, it reflects it, it absorbs it, or it transmits it. Okay. If the radiant energy is allowed to fall on the blackened metallic surface or a carbon black, it is found that energy is almost completely absorbed. So this is the property of blackened surface. So we always say that whenever we go in a sunlight, don't wear a dark clothes, don't wear a black clothes, always wear a light clothes or prefer to the white. Why? Because that black surface or that black thing absorbs the more radiation. This is a common thing that we think in our day-to-day life. Similarly, when the radiant energy is allowed to fall on a blackened metallic surface or carbon black, it is found that the energy is almost completely absorbed. Okay, a body which completely absorbs the radiant energy falling on it is called as a perfectly black body. So whatever the radiations that are falling on that black body get completely absorbed by that body, then that body is known as a perfectly black body. The black body radiate the maximum amount of energy for the given temperature. The radiation thus emitted by the black body are called as a black body radiation. Okay. So main point is the radiation emitted by the black body is known as a black body radiation. Is it okay? So the Kirchhoffs in 1859 stated that at any temperature the ratio of emissive power of a body to the absorptive power is constant. That means how much the body can emit or how much that body can absorb, that power is known as emissive power or absorptive power respectively. And the ratio of emissive power to the absorptive power is constant. Independent of nature of the surface and is equal to the emissive power of a perfectly black body. Okay. So now we will see the spectral distribution of black body radiation. So see, this is the wavelength of radiation and relative intensity. Okay. So with increase in the temperature, the energy radiated per unit area per unit time from any surface increases rapidly and simultaneously. So as we increase the temperature, the intensity of radiation increases. Okay, this is the common thing, that with increase in the temperature, the energy radiated per unit area per unit time from the surface increases rapidly and continuously. So according to the Stephens, in 1879 showed that the total amount of energy E radiated by the perfectly body per unit area per unit time is directly proportional to the fourth power of its absolute temperature. That means as the temperature increases by 1 unit or 2 unit, it's 4 times the energy increases. Is it clear? So this was according to the Stephens law. So these are some observations that are seen from that graph. At a particular temperature, the distribution of energy is not uniform among the various wavelengths of radiation emitted by the black body. For each temperature, there is a wavelength at which the energy radiated is maximum. That means for each temperature, there is a peak. After that, it decreases. The relative intensity of radiation gets decreased. Okay, and the wavelength is shifting towards the lower side. Yes or no? So, for each temperature, there is a wavelength at which the energy radiated is maximum. With increase in the temperature, the maxima shifts to higher intensity but towards the lower wavelength. See, I have shown you the shift. That the maxima shifts to a higher intensity. So intensity is always increasing of this peak. So here the intensity is low, it is increasing, increasing, increasing. But this maxima is shifting towards the lower wavelength. That is, increase in the temperature, energy of radiation increases, but the corresponding wavelength decreases. Okay. So you have to remember this point, which is important. As the temperature increases, the relative intensity of that radiation increases, but the wavelength shifts towards the lower. So the area under the curve for a particular temperature gives the total energy emitted by the black body per unit area per unit time of the complete spectrum. So area under this curve, that means under this curve, this is the area. So as the temperature increases, the area under curve is also increases. So what this area under the curves indicates? It indicates that the total energy emitted by the black body per unit area per unit time for the complete spectrum, it also get increased. So next is the spectral explanation of spectral distribution on the basis of classical mechanics. So what does the classical mechanics tells us about that peaks that we are going to see? To explain the curves, the Maxwell, according to the Maxwell's electromagnetic wave theory was applied. According to this, the source of electromagnetic radiation is the vibrating particle called as an oscillator, and these oscillators could radiate or absorb the any amount of energy. Okay, and according to the Wend's law in 1896, Wend's in 1896, Rayleigh and Jeans in 1900 tried to explain the spectral distribution of black body radiation. So Wein's law was applied to only the distribution at lower wavelength, whereas the Rayleigh-Jeans law was applied only for the high wavelength. However, neither of two was able to explain the complete spectral distribution of black body radiation. So according to the Wein's radiation law, E, that is energy, is equal to 8 pi hc upon lambda raised to 5 into e raised to minus hc upon k into t into lambda, where h is a Planck's constant, c is the velocity, k is the Boltzmann constant, t is the temperature, lambda is the wavelength. Now, according to the Rayleigh-Jeans law, E is equal to 8 pi upon lambda raised to 4 into kT. So, but this two law was unable to explain the spectral distribution of black body radiation. So, the next we are going to see the explanation of spectral distribution on the basis of Planck's radiation law. To explain the spectral distribution of black body radiation, Max Planck in 1900 proposed assumption that the oscillator of black body cannot have any amount of energy but can have only discrete amount of energy depending upon the frequency of the oscillator. So in the previous, according to classical mechanics, we have seen that the electromagnetic radiation is the vibrating particle called as an oscillator, and this oscillator could radiate or absorb any amount of energy. So there was a correction that it cannot emit or absorb any amount of energy but can have only discrete amount of energy depending upon the frequency of that oscillator. So Planck then proposed a radiation law. So what does this radiation law states? Energy is emitted or absorbed not continuously but discontinuously in the form of packets called as quanta, that we have seen in the previous. So the energy of that quanta is given as E is equal to h nu, where h is a Planck's constant, nu is the frequency of that radiation. So this indicates that E, that is energy, depends on the frequency of radiation. And according to the Planck's law, E of lambda, that is a wavelength of radiation, is equal to 8 pi hc upon lambda raised to 5 into 1 upon e raised to hc upon kt lambda minus 1. So this was the correction done by the Planck in this Wein's and Rayleigh-Jeans law. Is it okay? Is this clear? So here we will stop. Thank you.